Hello and welcome back to this online NPTEL course on aquatic geochemistry. We were discussing radioactive isotopes and we are going to learn how to calculate radioactive decay. A very important application of radioactive isotopes is to understand how radioactive decay is happening, how you can date different kind of matrices. You can date soil, you can date minerals, you can date water, you can date a variety of objects, you can date basically anything, okay, based on what kind of material is there. So, for instance, for minerals and all that, okay, we are going to use different dating tools, okay. If it is certain organics, okay, then we are going to date using carbon and all that. So, different isotopes are used as tools to date different kinds of objects. Okay. Same isotope system is not used because we are going to learn why. Okay. So, today we are in the previous lecture we learned about why the nucleus is not stable at some times, why will radioactivity suddenly happen. Okay. Today let us see how to do dating calculations. So, simple radioactive decay, okay, how do we calculate that? Okay. So, radioactive decay is a stochastic process, that means it is the most probable process. There will be a pattern, but you cannot exactly predict when it can happen, okay, and it is all linked to the stability of the nuclei. Now, this change when it is happening, okay, there is this rate called the decay rate. Okay. So, this has a constant term, so which we denote it with this symbol called lambda. Okay. So, if we first write this equation, then this dN by dt, that means the rate of decay is directly proportional to the number of N present. N is the number of parent atoms. Okay. So, N is the number of atoms, radioactive parent atoms present. Okay. It is directly proportional to N. Okay. To remove this proportionality term, we are going to add this lambda, we are going to add this constant term. Okay. And why is it a negative term? Why is here a negative? Because it is decreasing, right. We are going to decay it. Decay means it is going to decrease in its number. Okay. So, here we just rearrange. So, you bring n from here in the denominator and dt goes there. So, here on the left side we have all n related terms and on the right side we have all the time related term. Okay. Let us integrate it, integrating over a particular time period, say over 10 years, 100 years, we are going to do some experiment, right. So, we are going to integrate it over a time period. After integrating it from this time, we get simply this integration yields this one. So, you integrate dn by n, so you get minus log of n ln n and lambda t plus c. Okay. Now, c is again a constant term. So, we have to find out what is c. So, this integration constant we can find out by setting a value of my initial time equal to t0. Okay. At my time equal to t0, my number of parent atoms is equal to my number of initial parent atoms. So, at t0, okay, this is my number of atoms there that decayed to n within a time period of t. Okay. So, n equal to n0 at t equal to t0. Okay. If I fit in this value, then my c comes as minus ln 0, because t is equal to 0 here, right. T is 0 here, time is equal to 0 here. So, C comes as ln, C is equal to minus ln of n, and ln of n is equal to n0. So, C comes as minus ln of n0. Here in this equation now we are going to simply substitute that. Okay. So, minus ln of n is equal to lambda t minus ln of n0 value. Again let us rearrange, let us bring all the n terms together. So, this goes in this side of the equal to. So, ln of n minus ln of n0 is equal to minus lambda t. Okay. Here we are just going to rearrange and subtract with multiply with minus 1. Okay. So, ln of n minus ln of n0 is equal to minus lambda t. Let us again rearrange it. Since this is minus log of both sides, so you take ln in common, n divided by n0 equal to minus lambda t. Now, let us eliminate this natural log. Okay. So, as you take this ln to this side, it becomes e to the power minus lambda t, e to the power minus lambda t. So, n is equal to n0 also goes this side. So, n0 into e to the power minus lambda t, very very important equation. Okay. So, my number of current parent atoms is equal to my initial parent atoms into e to the power minus lambda t, and this is because it is decaying. Now, we do not know n0 value. Why? Because we did not know when we started how many n0 values were there, right. We are dating natural systems. Now, we are present, we were not present that time, right. So, we do not know what is the n0 value. So, we have to find a way to remove that n0 term. Okay, we have to find a way to remove that n0 term from that equation. But what do we know now? We also know something, we also know what is the daughter atoms that has been produced from that. Okay, we know the daughter atoms from this n0 term. So, n0 minus n will give me the number of daughter atoms, radiogenically produced daughter atoms. Okay. So, let us replace n0. Okay. We are going to replace n0. What is n0? n0 is now equal to d star plus n. Okay. And also n0, since here we see n0, n is equal to n0 e to the power lambda t, therefore, n0 is also equal to n to the power e to the power lambda t. You just simply bring it here. So, d star is equal to n e to the power lambda t minus n. Take n in common, e to the power lambda t minus 1, or if it is a very very small lambda, then it just becomes this. So, if we now measure the number of daughter atoms, it is going to be this value. So, initial number of daughter atoms there plus the radiogenically produced daughters. So, obviously, any system they will have some initial 1 or 2 daughter atoms which is naturally there in that system. That is my d0 value, and those that has been formed only from the decay. So, d is equal to now d0 plus this, okay, n into e to the power lambda t minus 1. Again, this is a very very important equation, d equal to d0 plus n into e to the power minus t lambda minus 1, and this is the basic of radioactive decay equation that is used for determining rocks, minerals, okay, isotopes themselves. And this lambda value, this has been experimentally determined for almost all unstable and radioactive nuclides. Okay. And how do we know this D0 values? So, from the same rock what we do is, from the same rock we are going to check how much is the, so for instance we are going to find out the age of a rock. Okay. Now, in this rock you are going to have different minerals. Okay. But in all the minerals they will have the same D0 value and they are all undergoing decay. The different minerals, okay, the different mineral patches, they will all have the different, they will all undergo decay. Okay, all the radioactive they will decay. So, there is a particular method that if you measure all the different minerals, then what you will get is at this particular time, that is T0, there will be this D0 value, okay, which will be same for all the minerals. Okay. So, when we are going to measure that, the different elements will be there, different minerals will be there. So, we have to start finding out what is the D0 value. So, when we are going to do an analysis any rock, okay, you have to analyze different minerals or the same mineral in different patches, and from that you are going to calculate this. Okay, you will see that they are all falling on one particular line, and that is my initial daughter atoms. That is my initial number of daughter atoms. This is called the isochron method. If you want to look into more, you can always go back and look into this isotope geochemistry book by William White and look into the isochron method. Now, let us see what is happening here. So, if I am plotting the number of atoms in terms of N or D, that means my radiogenic parent and my radiogenically produced daughter. My parent is simply going to decrease, okay, and here are the half lives. So, in x axis we have half lives. So, in the first half life the number is going to be its half, then its number is going to be its half, this is going to be half, 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 half. So, whatever its number will be, it will start having this exponential curve. Okay. Same thing for daughter, the daughter also is going to equally increase in their number. And you can see after the first 5 half lives, okay, the concentration becomes very negligible, the change is very low. Okay, after the 5 or 6 half lives it becomes very low. So, what equation you do have to remember is only this equation where D is equal to D0 plus n into e to the power minus lambda t minus 1, extremely important equation, because this is how we are going to write a radioactive decay equation. For example, if we are looking at this system of 87 rubidium that is decaying into 87 strontium plus electron, which is basically an electron decay, how do we write it? We write it in terms of this, right, we are going to write in terms of this. So, what do we write? We write 87 strontium, and you can see it is written in the form of a ratio. So, 87 strontium divided by 86 strontium. Why do we have this division of 86 strontium? That is because of two things. First, we are going to measure this, okay, in a system called an ICP-MS. Okay. Generally multi-collector ICP-MS. Okay. These are mass spectrometers. Okay. These are mass spectrometers. meters, and they are very good in measuring isotope ratios as compared to their particular whole concentrations. So, they measure isotope ratios in a much efficient way than the as compared to the total concentration, because remember their abundances are very low. Their abundances are very low. Okay. So, rather than finding the total concentration, what they very accurately measure is the isotope ratio. Okay. Plus this 86 strontium, okay, is an example of a non-radiogenic or stable isotope. This is a non-radiogenic or a stable isotope, and it functions as a reference point. Okay. It functions as a reference point because whatever increase is happening in 87 strontium value is just going to be from the decay. It is just going to be from the radiogenic decay. So, any higher movement, any higher value of 87 strontium by 86 strontium is actually showing us the decay of 87 strontium and not the lowering of 86 strontium. No, this value is fixed because it is an abundance value, it is fixed in nature, okay, and it actually acts as a reference point. So, any increase in value, it is actually showing that this radiogenic daughter has increased. Okay. This radiogenic daughter has increased. Okay. So, when we write 87, 86 strontium in present day plus its initial ratio, okay, 86 strontium, 87 strontium by 86 strontium initial, that is 0, plus this parent atom 87 rubidium divided by 86 strontium into e to the power lambda t minus 1. Okay. So, this is how we are going to write our equations when we have a parent and a daughter isotope ratio. Okay. Again, we use a ratio first of all because of our analytical issues, because measuring isotope ratios is far more precise and accurate as compared to measuring the total concentration. And second of all, it acts as a reference point because these are stable non-radiogenic isotopes and their values are fixed in nature. Okay. So, in our isotope geochemistry, in the application of understanding Earth's surface chemistry, there are certain isotopes which we are called radiogenic isotopes. So, we are going to look into this rubidium strontium, we are going to look into the osmium system, lead isotopes, okay, samarium, neodymium, uranium. So, the uranium, uranium series is a decay series. So, uranium finally decays and I think it forms lead. Okay. So, uranium has an entire decay series and there are multiple elements formed in between. Okay. Then there are other isotope system called the traditional stable isotopes, and stable isotopes and radiogenic isotopes are absolutely different. Radiogenic isotopes, their isotopes are formed mostly due to radiogenic decay. This entire phenomena of radioactive decay. But in stable isotope geochemistry, no such radioactive decay is happening. Okay, they are all stable isotopes. For instance, you will see the traditional stable isotopes will have hydrogen, it will have carbon, nitrogen, oxygen, sulfur, and that is because they themselves, their occurrence in nature, their isotopes has a variation. For instance, there will be hydrogen, they will be in the form of protium, deuterium and tritium, and their abundance is not related to any kind of radioactive decay, they are just there. Okay. So, they are all stable isotopes and their occurrence is fixed in nature, and their occurrence is not due to any kind of radioactive decay phenomenon. It is just how they are present in nature. And one of them is called traditional and another group is called non-traditional. Which is the traditional one? Traditional one is a group of elements which I have already said, hydrogen, carbon, nitrogen, oxygen, sulfur. Okay. This group of elements has already been studied extensively for the last say 40 years. Extensively they have been studied. So, they are called the more traditional ones, they are very used traditionally, it is like using that particular term. So, it is very commonly used isotopes. What are the non-traditional stable isotopes? So, now with the advancement of technology, with more complicated machines, instruments coming up, we can now measure with a lot of accuracy certain other metals also, who also have a lot of variability in their natural isotope abundance. For example, lithium. Okay. So, lithium also will be having 6 lithium, 7 lithium, 8 lithium. Okay. Their abundances will also vary in nature. Okay. Now, we have the instrumental ability to measure this. Or for instance, take iron, for instance take copper, for instance take zinc. Okay, so, zinc will have 63 copper and will have 65 copper. So, you can measure both of this, you are just going to measure the natural abundance, their variation is just due to natural processes, and the variation, okay, their variation is caused due to processes that they are undergoing as compared to radioactive decay for radiogenic isotopes. Try to understand this difference. In radiogenic isotope systems, radioactive decay is causing the change in the number. Okay. Say today you measure 87 by 86 strontium, you measure X value, you measure 50 years later it will be a Y value. Now, this change is because of the radioactive decay. This is not due to some other processes, this is not due to any process that this is undergoing. This is because 87 rubidium is decaying into 87 strontium. But in terms of copper, these isotopes are not formed due to decay. Okay? They have a natural abundance. Their differences is due to the process related, and we are going to look into why it is called process related and mass dependent fractionations and all that. Same thing for lithium, hydrogen. Their differences in number, if you are measuring, is due to the processes that they are undergoing as compared to radioactive decay. So, the fundamental difference between radioactive isotope geochemistry and stable isotope geochemistry is what they are dependent on. First, radioactive decay controls radioactive isotopes, and radioactive isotopes also sometimes show mixing of two different sources if they have different originating time, which is again very important application in aqueous chemistry, which is why it is applicable in aqueous chemistry. Not because of radioactive decay, because we are not going to date a lot of water, but it is because of this mixing of two different processes of sources is what is going to be very applicable in aqueous geochemistry. Stable isotope geochemistry has rather more applications, because their signature depends on the physical processes, on the chemical processes and the source related mixing. So, they can actually infer all of these. Okay. From this isotope system we can infer all of this. But again you see, with increasing number of processes, the chances of them separating it out, whether it is a source mixing, whether it is physical process, whether it is chemical process, also becomes difficult. Because for instance, in aqueous chemistry, if you are measuring radioactive isotopes and if things are changing, we knew it is some kind of mixing has happened. Because in the time scale that we are looking for, there will not be much of a radioactive decay. Okay. There will not be much of a radioactive decay. So, the most likely thing is there will be mixing of two sources. But in case of stable isotope geochemistry, when there is some physical process that we are targeting, then we have to use some stable isotopes. When we are targeting particular kind of chemical reactions, we have to use stable isotopes. When we are doing mixing of sources which has very particular different kind of source signatures, then we should use stable isotopes. Okay. They go mass independent fractionations. Remember these terms, they undergo mass independent fractionations. Their fraction is mass dependent, that means whatever is the mass difference, they carry a lot of effect on how they are fractionating in between the phases. And what I mean by this complicated terms which might seem right now, I will explain in the future slides. So, for example, let us see some application of isotope geochemistry. So, the first thing that we obviously have talked about is dating of a sample, and that entirely forms a new branch of study called geochronology. Okay. And in this geochronology, we apply a lot of different types of isotopes, okay, a lot of elements based on their half life period, okay, based on their half life period value. For example, when we are trying to date water, we are going to see if it is getting recharged or not, or all that. Very often you will see this tritium measurements, okay, because their half life is 12.32. And they are very much in the time frame where all the hydrological cycles specifically for groundwater is happening. Okay. So, this kind of time frame which is very close to a decade, very useful, okay, as compared to for some another kind of study which might be related to ice cores and all that. There what we are going to use, we are going to use 10 beryllium. Okay. That kind of dating gives us when that particular ice core if we are trying to date an ice core and all that, we are going to go for 10 beryllium. Okay. So, for different kinds of applications, okay, for different kinds of applications, we have different kinds of isotopes, and as you can see that their half life is very variable. It can be as low as 0.24 years, very short lifespan, to as high as this one, okay, very long lifespan. Okay. So, when we are going to do our science, we have to understand, okay, what kind of time scale we are looking for. It is some small time scale, then we are going to look for tritium or sodium, or is it going to be a very long time scale, then maybe we have to use our 26 aluminum or 10 beryllium, or if it is some kind of organic related, then we have to use organic isotopes, carbon we have to use. So, this kind of application is very much you have to understand what processes are happening, what is your material that you are going to date. So, based on that you are going to select your element. With this I come to the end of this lecture today, and we are going to continue with radioactive isotopes in our next lecture. Thank you.